Okay, welcome back. This is preliminary chapter 2 for the video lecture series for Calculus 1. And in this particular video, we're going to be discussing the concept of a limit, because calculus is possible to understand, although very hard to understand if you don't have that concept. So the easiest way to think about a limit and to kind of get a handle on what this thing is, we are not going to be talking about the notations and the specific analytical methods for evaluating the limits, although I will show you one or two that are kind of famous. Really, what the purpose of this preliminary chapter is just for you to get an idea as to what a limit is. So that when we start talking about these things and the concept of the derivative in the later chapters, that this you have something to stand on. So there's a few terms that we need to discuss first. And first of all, we're working towards the definition for a limit. But first of all, what I wanted to do is just a quick reminder from maybe an Algebra 2 course or a college algebra course. There's a few sections that have to do with these. The word sequence and series, and I wanted to just quickly show you what that is because they're the two examples that I have on the board at this time. So a sequence is just any list of numbers in some sort of order like this. 1, 3, 9, 27. This is a sequence of numbers, and the little ellipsis on the end, the dot, 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 that just means that this is going to continue going, following the pattern established by that sequence of four numbers. And typically, infinite sequences that have this ellipsis on the end, this just means that we could continue listing terms. The next one is 81, the next one after that's 243, and so on and so forth. And we could do this forever if we knew what particular function generated that sequence. So if you look at this type of sequence, we could have two different situations that happen here, and there's two other sort of definitions we need to establish before we go forward. A sequence will either kind of approach a number. It'll get really, really close to it in Algebra 2 and ISM 1 college algebra. We would call that sort of like an asymptotic behavior, as in it will gradually tend to get really close to a certain number without ever touching it. And this is the really loose sort of definition that college algebra used, but that's something that was taught to you and that we have a pretty firm grasp on. And really what that definition says is what a limit is in its short forms. We're just using a slightly different word to refer to a concept that we already sort of understand. Now, the other thing that you notice from college algebra is that there are many functions which go wildly off screen to the right or wildly off screen to the left, and they don't really actually approach a number. So we have these two different words which we use to describe that type of behavior. And if you have some function, for example, something that looks like this, then as this goes really, really, really far, as this graph goes really far to the right direction, what you'll notice is that the orange line here just goes flying off towards infinity. The numbers just continue to get bigger forever and ever and ever without bound. And actually, if you look at this first example here, that's exactly what we have. We have the sequence 1, 3, 9, and 27. And there's plenty of techniques for discovering what particular function generated this sequence, but this is a geometric sequence. That is that each number is generated by multiplying the previous number, in this case by 3. So you just repetitively multiply by 3 over and over again, you get this sequence. Now notice that multiplying by 3 has the effect of making things bigger. And so since this is going to make a natural number bigger and bigger and bigger and bigger, then we would say that this particular function will just continue to increase without bounds, which is sort of the situation that we had with this graph right here. The word we use to describe this, if a sequence of numbers just continues to get bigger or smaller without bound, and what I mean by without bound is that you can't tell me how big it ever gets because I can always just multiply by 3 and make it bigger still. Then the word that we use to describe that is that this sequence diverges. Okay? So the second sort of term that we need to discuss not only is sequences, but what if you take all of the elements in a sequence? So we had 1, 3, 9, 27, blah, blah. What if we take all of that sequence of numbers and we add this together? Well, that has its own term as well. That's called a series. That's the action of taking a sequence and then adding all the individual terms together. Now we have finite series and we have infinite series, and you notice that when the sequence like this has an ellipsis on the end, then of course if we were to do a series with this particular sequence, we're adding together an infinite number of terms. And there's this nice little trick where if the sequence tends to diverge, well then the series will also tend to diverge, because if you notice I keep getting these progressively bigger and bigger numbers. So obviously when I continue to add bigger and bigger numbers, I can make this series as arbitrarily large as I want, and as a result it diverges. Okay, so that is kind of, you have a good handle on what a sequence is. It's a list of numbers. We know that a series at this point is just when you add the individual elements of a sequence together and then you look at what the result is. And we have two words that describe the behavior of those sequences and series, and consequently I used an example with a graph as well. Those words can be used there as well. Diverges is the easiest to understand. This is something getting bigger or more negative, I should say. I don't want to say smaller, because we're going to see an example where that's not entirely true in just a second. So it'll either just continue to get more positive without bound or more negative without bound. Then we say that the sequence or series diverges. Now in example 2, we have a slightly different case here, and I'm actually going to derive this one for you. I'll write in diverges just for my own sanity there. So in this second example, you'll notice that we have this series presented to us. Now you could choose to write the individual terms of this sequence if you wanted to, and we usually do that in like a little brace or something of the like. Some people just list the terms. It just, depends on who you are and what your preferences are. But this series was constructed out of the sequence 1/2, 1/4, 1/8, 1/16, and so on. And what you'll notice here is, again, we have a geometric sequence, and because it is geometric, we can produce the next term by doing some uniform multiplication over and over and over again. So if we start with 1/2, we can get to 1/4 just by multiplying by 1/2. And if we have a 4th, then we can get to an 1/8 by multiplying by a 1/2. And another way to say this is I'm just taking every single term and I'm dividing it in half. So like I'm just repetitively taking half of the numbers over and over and over again. If I take half of it, you get a 4th, take a 4th, take half of it, you get an 1/8, you take an 1/8, you take a half of it, you get a 16th, and so on and so forth. So then we have this series here, which is where I'm going to add the individual terms in the sequence together. And we want to look for what the other word that describes the particular behavior is. Now, what I want to do real quick is just kind of show you what this graph might look like. So a graph of this particular sequence, if I say that this is 1 up here and this is a 1/2, then when I'm at step 1 in the sequence, which is the first number in the sequence, I get a little dot here, and then I get half of it, and I get half of it again, and I get half of it again. And if I were to connect this together into sort of like a continuous sort of function, what you'll notice is you get something that looks like this. And the specific feature that I want you to kind of have in mind here is that as I go across forever in the right direction, that is, I keep looking further and further down this sequence, what's the next term, what's the next term, what's the next term, what's the next term, we get this nice horizontal asymptote feature. And that's kind of a giant red flag that what we're going to have is the other case where the series does not diverge, but it's going to get really close to something. And sometimes this is true and sometimes this isn't true. At the bare minimum, it does mean that the sequence is not going to diverge, but the series could do one thing or the other. So I'm going to actually derive this one for you because I think it's a nice algebra exercise. So suppose that we take our series here and we want to know what this addition, this infinite addition, should equal to. Well, what I have is 1/2 plus 1/4 plus 1/8 plus 1/16 over and over and over again. And I'm going to just say that this is equal to s. In other words, the sum of all of these numbers, I'm going to put that into the variable s, and that is 1/2 plus 1/4 plus 1/8 plus da da da. Okay. Now notice that if I take both sides of this particular equation that I've developed, and I multiply it by 2, then what I should have is 2s is equal to 2 times 1/2, which is going to be 1, plus 2 times 1/4, which is going to be 1/2, plus 2 times 1/8, which would be 2 over 8, which is 1/4, plus if I do the same exercise with a 16th, if I do the same exercise with a 32nd, and so on and so forth, we should very quickly notice that we have this portion right here, which is the same sequence that I began with. That's 1/2 plus 1/4 plus 1/8. We just got this extra 1 right here. And because this continues forever, notice that this part right here, which I've underlined in this orange color, is actually the same size as the original statement. So what we have is actually 2s is equal to 1 plus, well, what is all of that stuff underlined in the orange? Notice that the original statement was that s is equal to all that stuff in the orange underline, so I can just replace this entire orange underline with s. Now if I very quickly do some algebra here, I can take away s, canceling it off of the right-hand side, leaving me with 1, and in other words, s is equal to 1. Now, when I'm able to find a specific number that this series goes towards, then what I say is not that the series diverges, it just gets bigger or more negative without boundary. I say that it converges on a specific number, and that would be the answer to this series. Okay? So what a limit is it just looks, at its heart, it just looks at what the sequence of numbers is doing in a sort of general location. So in this case, I was specifically concerned with what happens on the end. So 1, 3, 9, 27, what happens when I keep going? It gets bigger forever. The limit is infinity. When I look at this sequence, what happens when I keep going further and further and further down the line? Well, notice that 1/2, 1/4, 1/8, 1/16, and so on and so forth. If I just look at this sequence, these numbers get particularly small, and I had that horizontal asymptote sort of behavior at 0. So that sequence is going to get really, really, really close to 0. But what happens when I add all these terms together and I keep going forever and ever and ever and ever and ever? What happens to that? That's what the question of the limit is trying to answer. What is this going to do when I add all these things together forever? In this case, it does not diverge. It converges because I'm able to find a number that this goes towards through some trickery. And if you don't follow the trickery, that's fine. That's why you're taking calculus. But when I can find a number, then we say that it converges. At its heart, a limit is just going to ask that question and answer that question. There's a lot of little analytical techniques that we use for this, but we do that a little bit later on. The reason that you need this is because in the next preliminary chapter, we're going to be discussing the concept of the derivative, and the derivative happens to be a special type of limit.